Hi everyone, Jean Kirapinha, thanks for connecting. The purpose of this video is to take you over the last module in the Applied Pharmacoeconomics course, and this video will be reviewing decision analysis and dealing with uncertainty. Just because the field of pharmacoeconomics, particularly the costs and the outcomes that we're using, there's always a degree of uncertainty, a probability associated with specific inputs that are used in pharmacoeconomic analysis, varying between clinical practice settings, between countries, between hospitals in the same country, or even in the same city. So it's dealing with uncertainty is very much focused on the variability of different input variables that are used in the pharmacoeconomic analysis, and this applies to all different methods that we've covered in this course so far. It applies to cost effectiveness analysis, cost utility, cost benefit, because the costs and the outcomes, whether it's monetized or whether it's measures of effectiveness or whether it's quality adjusted life years that are based on utilities, all of these are variables, so they vary in different situations. So what we do in pharmacoeconomics is we need to find a way of dealing with uncertainty, and this is the purpose of the video today. So a few objectives based on chapter 9 in the prescribed textbook are 5 in total. I want to talk about a definition and the purpose of decision analysis that I've already just started briefly to introduce that. The second is to list the steps for performing a decision analysis that are quite elementary. So there's only 5 steps or 6 steps in total, starting from identifying the specific decision and all the way through to the final step, which is doing the sensitivity analysis. And on that point of sensitivity analysis, I'll spend a number of minutes just going over the methodological components, the kind of the logic applied to sensitivity analysis. The third is to explain the use of a decision tree. We haven't covered this concept yet, so this is fairly new. Look at the calculation of the average costs and the outcomes from a decision tree, so I'll take you through how to do that, and then finally is interpreting a threshold analysis graphs that were presented in the textbooks and how to apply them. So let's move straight into looking at a decision tree structure. In the textbook, it describes 6 steps in total for putting together a decision analysis, and you may recall that at the beginning of this course we discussed the structure of a pharmacoeconomic question, that it had to have the comparators, the different alternatives, a delineation of the costs and the outcomes, a perspective, and so there were all those key components. What a decision tree is doing, decision analysis, this process is presenting in a graphical form a tree that presents all the different alternatives, pathways associated with 2 different alternatives. So a decision tree always comprises of nodes, so which is the solid square box, the kind of the open circle over there, and then the triangle lying on its side. Whenever you see a square, that refers to a choice, so that's a choice node. Whenever you see a circle, that is a chance node, and whenever you see a triangle, that's a terminal node. A choice node is that when you are entering the pharmacoeconomic question, your point of departure, if you're evaluating infection, for instance, and this scenario is about antibiotic A compared to antibiotic B, the choice node suggests that when you are entering this point over here, you have to make a choice. You've got to make a decision between using 2 different alternatives that are being compared. Either you choose antibiotic A or you choose antibiotic B, and that's the reason for calling it a choice node, because you have to make a decision. Either you go for A or you go for B. Doesn't mean that you can't have other options. You could have an antibiotic C, D, E, F, as many options as you want. The increase in the amount of comparators and interventions, the increase in the level of complexity and the interpretation of it. But at a minimum, a pharmacoeconomic analysis will include always 2 comparators, irrespective of the method, whether it's as I mentioned, cost-benefit analysis, or cost utility, or cost effectiveness. So there's a choice node, and then once you have made a choice, let's say you've picked to use antibiotic A within the hospital environment, then there's a chance or a probability associated with the use of antibiotic A that you'll have a clinically successful outcome, or there'll be clinical failure, right? So those are the node at this point over here is called a chance node, because you are not certain of the outcome associated with the use of that antibiotic. So because you're uncertain, there's always a probability associated with a successful treatment or clinical failure. Those probabilities, where you get them from is your clinical trial, and that they will have measures of effectiveness. They need to be converted into probabilities that are applicable for the use in decision trees, and also the time frame. And there's a certain process that you have to go through to calculate those transition probabilities. It's beyond the scope of this course to discuss that particular method, but just to let you know is that those probabilities are extracted from the clinical trial, and they are used to define these different arms. So that is a a chance node, because there's a probability associated with clinical success and clinical failure. There's an uncertain outcome over here, and that data comes from the clinical trials. Then there's a further chance node as you progress down this arm of using antibiotic A, achieving clinical success, but then there'll be a group of patients that experience no adverse events and some that do. Again, you aren't 100% certain of what the proportion is going to be between these two, or there remains some degree of uncertainty which patients would experience an adverse events and which would not. So again, you're faced with a chance, a probability of splitting this clinically successful group into those that experience an adverse event compared to those that do not experience an adverse event. So again, there's another chance node. And when these branches of antibiotic A and clinical success and no adverse events, when it ends, it is displayed, it's illustrated with a triangle. So that's either the terminal node. As soon as you see that, it means that this pathway has ended, so there are no further costs or utilities or outcomes associated with it, and this is where you want to stop the analysis. Let's imagine a different pathway where you choose antibiotic A, but then there's a probability of clinical failure, so you come into this arm, but then there's a chance that you will experience an adverse event on clinical failure, for instance, but then the analysis stops there because there's a terminal node. And the same logic of chance node versus terminal nodes applies then to your bottom option. Usually there's a mirror image, so if you put a mirror up here between your antibiotic A and antibiotic B, is what you see above is what you should see below. It is not always the case, particularly in oncology, for instance, or cardiovascular disease, where the events associated with the use of antibiotic A are different compared to antibiotic B, so you will see some differences in the structure, but broadly speaking, you should see a mirror image of the two, and it's very much dependent on the therapeutic area. These are referred to as branches and arms of the branch. If a patient is provided antibiotic A, clinical success, and no adverse event, this particular path that the patient experienced or was on is referred to as a pathway. And then there are costs and outcomes associated with each of these pathways. Is that if you pick antibiotic A, there's a cost associated with using antibiotic A. There's a cost for clinical success too, and there's also a cost for adverse events and no adverse events, and also adverse events. If you go down a specific pathway, the total costs is the summation of the costs associated with each of these states. No adverse event, the cost of that. Add to that the cost of clinical success, if any, and add to that the cost of the antibiotic, if any. And the same thing applies to antibiotic B option. And then there's also outcomes associated with each of these, either in the form of a utility or a monetized benefit. A patient that uses antibiotic A achieves clinical success and has no adverse events. If we're doing a cost utility analysis, the utility associated with that pathway would be lower, presumably, compared to a patient that achieved clinical success but experienced an adverse event where the utility value would be lower. And likewise, patients that achieve clinical failure, very likely that they would have to be initiated on another antibiotic, and if those that experience an adverse event, then the utility is even lower. So as you can see, the kind of the scenarios that build off of this heading into the future suggest that the utility values associated with clinical failure is going to be lower compared to the clinical success. So the costs and the outcomes are very much dependent on the pathway associated with the different states. Next is the probabilities. I mentioned that associated with the chance node is an uncertain outcome, but there are probabilities associated with a clinical success versus clinical failure. These chances, the probable events that flow out of the use of a specific intervention, these two events need to be mutually exclusive in the sense that there can't be any overlap. Clinical success must be there must be a very specific definition for what clinical success is. There cannot be any level of ambiguity or overlap in the understanding of what clinical failure is. As soon as they are not mutually exclusive, these cannot be considered as independent states. An important principle applies there is that the probability of clinical success, let's say at 0.8, suggests that if these two events are mutually exclusive, then the probability of clinical failure has to be 0.2, which is 1 minus the 0.8, which is 0.2. What does this mean? It means that the summation of probabilities that flow out of a chance node must sum to a total of 1. It's just the law of probability. It's just the way it is. You can't achieve a probability greater than 1. And if you had further branches coming out of the chance node, then the total of the probabilities associated with branch number 1, branch number 2, branch number 3 must again total 1, and also the different states that come out of a chance node must also be mutually exclusive. So that's an important principle. Okay, so let's head over to the next slide. So these are some calculations on how to use decision trees. You'll see that the core structure of this decision tree is what we just discussed in the previous slide. So precisely the same interventions, the same possible outcomes associated with this chance node over here, also adverse events. But now there are costs associated with this pathway. So $600 US is the cost associated with success but no adverse events. The cost associated with this pathway over here, adverse event, clinical success, antibiotic A, is $1,600 US because most likely the cost of managing this adverse event is a lot higher compared to no adverse event. And you'll see the same logic then applies, that the cost of no adverse events is less compared to managing adverse events, and the same thing for antibiotic B. In this instance, the cost is lower for managing patients with no adverse events compared to the cost for patients that experience adverse events. However, the difference between antibiotic A and antibiotic B is the probability of success. You'll see that these probabilities are listed just below the state. It can either be there or can be here on the side, but by convention it's usually just below the state name. And for antibiotic A, the probability of clinical success is 0.9. Compare this to antibiotic B, it's 0.8. Because these two states are mutually exclusive, then the probability of clinical failure is 1 minus 0.9, which is a 0.1. And likewise, the same logic applies here at the bottom. These two states are mutually exclusive, so 1 minus 0.8 is 0.2. So that's a probability of clinical failure. So there's that level of difference. There's also a difference in the probabilities of no adverse event compared to adverse events. Rather, let's work with the probability of adverse event amongst those that are clinically successful. It's 0.1. Compare that to antibiotic B is 0.15. Again, this data is coming from your clinical trial, and you're using the different event rates, converting it to probabilities, putting it into the decision tree, and using that as a basis for the calculation of your expected values. Right, so how to use all of this data, and the purpose of presenting these decision analysis in a graphical form is fundamentally you want to make a choice between either utilizing antibiotic A or antibiotic B, right? That's the purpose of pharmacoeconomics. And in this instance, we've got costs input into here, so we want to find which of these pathways is the least costly intervention. And the way to do that is to calculate the expected cost associated with the chance node. And the way that is done is, here's antibiotic A. So let's see, the cost multiplied by the product of the probabilities in that pathway. So the cost we already know is 600. What is the expected probability of this pathway? Is 0.9 multiplied by 0.9, which is 0.81. So it's this calculation here at the bottom. Because what we're aiming to do is calculate the total probability of this pathway associated with the cost. So we've already got the first piece of data, 600 total cost for that pathway. And not for the pathway, excuse me. No, that's right. So 600 total cost for the pathway, and if you we already have the cost for this pathway, adverse event, clinical success, antibiotic A, 1,600. The probability for the pathway is 0.1 multiplied by 0.9. That is equal to 0.09. So that's that probability over there. Let's continue. We get the probability then for the pathway number 3, which is 0.9 multiplied by 0.1. That's also going to be equal to 0.09. And 600, we already got the cost. And then this pathway number 4 is 0.1 multiplied by 0.1, which is 0.01. So you have the 1,600 and the pathway probability of 0.01. So these are these calculations here at the bottom. To calculate the expected value associated with that pathway, which then becomes an average cost, is the 600 associated with this pathway, that cost, multiplied by the pathway probability, which is in this instance 0.81, this figure over there. So 600 multiplied by 0.81 is 486. 1,600 multiplied by that figure is 144. 600 by that one, etc., etc. Then the total expected value at this chance node over here is the sum of all of the expected values for the pathways, 486, 144, 54, 16, and the total expected value, average cost for antibiotic A for a patient is $700 US. Okay. This expected value over here at the chance node is compared to the expected value that you get for antibiotic B. The exact same process is used for pathway 5, 6, 7, and 8, taking the costs multiplied by the probability in the pathway, obtaining the product, summing those expected values, and then you get your final expected value at your chance node. What you're doing then is comparing the expected value at the chance node, 650, to the $700 US for antibiotic A, and choosing which is either lower. So in this instance it's antibiotic B, it's $50 US lower compared to 700, so you're going to be choosing antibiotic B. as your preferred option, as your least costly option. So, and this is just taking costs into account, right, and the probability of success. This is a useful way to analyze the two different comparators, and then also enables us to take one additional step is to calculate the incremental cost effectiveness ratio. We've already covered this in previous modules. It's the delta costs over the delta outcomes. I've put this in a red box because there's an error in the textbook. It should be the difference in the outcomes is 0.9 minus 0.8. The difference in the outcomes is a probability of success of antibiotic A, which is a 0.9 on top here, minus the probability of success of antibiotic B, which is a 0.8. So that's the reason for the denominator here. The difference in the expected costs is the $700 in that chance node minus the 650 expected cost in antibiotic B, and that is in your numerator. $50 divided by 0.1 is a total of $500 more per extra success that you're paying. Extra success defined in terms of extra success in clinical success, right, per additional patient that achieves additional success. So that is the way to roll back a decision tree, and the reason you see these two little lines over here is that the preferred pathway, that is blocking that pathway, so it's kind of cutting off this option over here. Antibiotic A is not the preferred option. That pathway has been cut off. The preferred path that you walk down or that you choose is going to be antibiotic B. And you can see that it's kind of bold as well. There are a lot of computer programs that assist in structuring decision trees, and some of them have differences in how they're presenting it. This is an example, a stylized example that you will most likely see in the software that you use for doing pharmacoeconomic analysis in the future. Right, so which gets us onto a discussion to consider uncertainty and the variability of different inputs. As I mentioned, these clinical success rates comes from the clinical trial, and it refers to the average patients or the average success rate across the sample in the clinical trial. But not every patient achieves that clinical success rate, and there's always a standard deviation or a confidence interval associated with that clinical success rate. So what we want to be doing in pharmacoeconomic analysis is including those variations in the economic analysis to determine under which circumstance would your decision change if your clinical success rate dropped as low as 0.5 probability, for instance, or even as low as 0.1 or even lower. And that is the core question, and the reason for sensitivity analysis is taking the baseline or the base case inputs that have been used in the pharmacoeconomic analysis. So the base case inputs are so those were provided in the textbook. It's the cost of the drug, cost of the adverse event. So what were those costs? For example, the cost of antibiotic use for antibiotic A was $600. Antibiotic B, the cost there was $500. The cost of treating an adverse event for these branches over here in this particular pathways was $1,000. So those base case figures refers to as a departure point, right? Your original position. And then what you do is you take each of those variables and you vary them. You provide a low estimate, you provide a high estimate. For example, the cost of treating an adverse event, I just mentioned the base case was $1,000. In this analysis, the low estimate was $500. The high estimate $2,500. And the purpose of doing this is taking that low estimate, putting it into the economic analysis, which is this decision tree over here, substituting that figure, and then calculating the overall cost for antibiotic A, which is $650, antibiotic B, $575, and determining what the difference is between the two. Taking then the high estimate, $2,500, putting that again into the pharmacoeconomic analysis, and seeing what your results are, 850 compared to 875. And what's the purpose of doing this? Typically, researchers will take the cost, they'll take the outcomes, they'll take the probabilities, they'll put it all into the sensitivity analysis calculations, the kind of the what if scenario building. What if the cost of treatment adverse event were to halve from 1,000 to 500? What if the cost of treating adverse event in a hospital, in a different hospital, is 2,500 compared to 1,000? So it's these what if scenarios that is the basis of using the sensitivity analysis. And the reason you do it, to kind of get to the point, is to estimate amongst the different variables that are included in the sensitivity analysis, the cost, the probability, which is the most impactful on the outcome and the final result of the economic evaluation. And in determining the one that is most impactful, is there a point where the decision of choosing A versus B changes? So this is a tornado diagram. It doesn't really look like a typical tornado diagram, but usually there's a funnel shaped. The most impactful variable in the sensitivity analysis is always listed at the top. The second most impactful, second from the top, third, fourth, and the fifth. So this is the base case, the original position 650. That's the purpose for the dotted line. And what you typically see is a tornado, right? Kind of like an inverted pyramid, starting from most impactful at the top to least impactful at the bottom. And the ranges suggest that entering the low value and the high value, that this is a total range of possible results that arise because of that variability. And this is the nature of the sensitivity analysis, or the purpose of it is to help decision makers in changing the inputs and determine at what point does a decision change. So this solid bar that you see here is where the decision changes. Anything below, anything to the left of this bar in this particular situation, antibiotic B would have been the preference. Anything to the left of it, it would be antibiotic A would have been the preference. And I'll get back to the reason for that in just a couple of moments. If you see a solid bar where there isn't any switch or a change in the decision, it means that the results are robust. There's always a preference for antibiotic B in this instance, so left to that. But you can definitely see from a decision analysis perspective what the range of possible outcomes could be if you change your inputs of probability, costs, and the outcomes. Changing one variable at a time is called a one-way sensitivity analysis. One way just suggesting that you're only changing one variable at a time. If you're changing two variables at a time, then it's called a two-way sensitivity analysis. It becomes a little bit more complex to interpret, but it is manageable. If you're doing a three-way sensitivity analysis, then you're working in a very different space, a three-dimensional space where three different variables are changing. It becomes a little bit more complex to interpret, not typically used. So you have to choose which variables you want to be varying, particularly in a two-way sensitivity analysis. And the textbook does present an example in a little bit more detail on page 176, so you may want to review that. So tornado diagrams are there to present a series of one-way sensitivity analysis to facilitate the graphical representation of which is the most important variable to consider, and where does the decision change from antibiotic A to antibiotic B. And this is the purpose of threshold analysis. And the idea here is taking the variable cost of an adverse event, so cost of treating an adverse event here, base case mentioned was $1,000, low estimate 500, high estimate 2,500, and this is what the x-axis is showing: 500 low estimate, 2,500 upper estimate, and the variability of that input, right? The expected value are these results that you're getting over here. The intersection between the two is where the expected value of the two options are precisely the same. So just to get back to expected value, it's when this chance node value is precisely the same as this chance value node. And let's say that they were both 800, for example. Well, how do you choose? Expected value for antibiotic A is 800. Expected value for antibiotic B is also 800. So it's really impossible to choose unless you work with other decision criteria beyond this decision tree to make that decision, which is not usually the case for the purposes of this discussion. So when it's the same, that's the point of intersection. So this is what that is referring to. Intersection of the line for antibiotic A compared to the intersection for the line for antibiotic B. And that expected value is at a cost of or cost of treating an adverse event of $2,000. Okay, so that's kind of the point of balance. And the point of using this is to find under which scenarios would you choose antibiotic A compared to antibiotic B. And the way to do that is, if the cost of managing an adverse event, okay, this portion over here, is less than $2,000, then you want to minimize the expected value and choose the line that is below the other one, right? If there's two alternatives over here. So minimizing the expected value, minimizing the cost, the average cost associated with the intervention is the objective in the economic analysis. So you will be picking antibiotic B. However, as the cost of managing the adverse event continues to increase, and as you get closer to 2000, there's a point of indifference, kind of a point of balance over there, and antibiotic B continues. However, the overlap suggests that to minimize the expected value, any cost of managing an adverse event above $2,000 suggests that you should be picking, from an efficiency perspective, you should be picking antibiotic A. Okay. So it is about minimizing the expected value, finding where the overlap between the two values are, and at what cost that is, and what expected value. The expected value, if you kind of draw a horizontal line to the y-axis, you'll get to approximately $800. And this is how you use threshold analysis, and it's very useful from a reimbursement decision making perspective if you are a health technology assessment agency, or if you're working for a government-based agency and you're trying to make a decision how the cost of managing adverse event across your network of hospitals may impact your choice of antibiotic. This is how you would use threshold analysis. Or if you're a health insurance company or a PBM, for example, you know that the cost of managing an adverse event is not the same across different hospitals or different pharmacies. So you want to be as flexible as possible in choosing the most efficient option. And the most efficient option is picking the pathway, picking the intervention that is least costly from an average cost perspective. So in this instance, it would have been antibiotic B, 650. You would pick antibiotic B if the cost of managing adverse event is below 2000. As soon as it crosses over, then you're going to be picking antibiotic A as your preferred choice. So that is the purpose of sensitivity analysis, right? It's fairly straightforward, fairly simple, fairly methodical in identifying the lower estimates and the upper estimates. How this is done, it can either be done on a purely scientific basis, so you use your clinical trial, you use your standard deviations, your confidence intervals, you put it into here, and you use that as your lower estimate and your upper estimate. Or it can be fairly non-scientific in the sense that you just halve your base case and you double your base case. I've also seen a lot of that, and we have used it in the past, especially when we don't have when there's missing data or we don't have the statistical values to use. And then just going through the calculation process and developing this threshold analysis and presenting these figures. In the textbook, as I mentioned a little earlier, is an example of a two-way sensitivity analysis. The logic is very similar to what I presented in this one-way sensitivity analysis. So just be sure to go over that and familiarize yourself on how to interpret that figure. It was figure 9.6 on page 176. So thanks so much for listening. Hope this helps, and let me know if you have any questions. Take care. Bye.